Ohayo gozaimasu, or good morning as my Japanese friends would say. We are finally to the point where we're going to complete, hopefully, the tachometer project I've been working on for a while. There's been several previous stories related to this tachometer project. We covered the sensor that we're using, a photoreflective sensor, RPR220. Then we covered the round display. I still got that set up here on the bench. That's used in the tachometer. Just an intro to that. Then I demonstrated how you could create a unique looking font for it so that you give your object or your device a custom look, so to speak. Well, now we're down to the final steps. And here I'm going to show you the components that we've got. Of course, we're 3D printing this stuff, and I'll have the files like I always do, the schematic, the source code for the Python source code, and etc. That'll all be on our companion website, which I'll have a link to down below, as well as links to the associated videos. But this is the completed project. This is what it looks like. This is the tachometer housing, 3D printed. I'm going to talk about that a little bit more here in a short while, but you'll recognize the font on the tachometer, and I can kind of make it operate a little bit here by tapping the sensor, pretending that it's getting a signal, and it works out real nice. And this white plastic component here has the RPR220 pickup sensor on it, and this will all get attached to this drill press that I had built a couple of years ago. It's 12,000 RPM spindle, I believe. It's got a very small collet in it. It works great for doing real precise drilling. I use it a lot for circuit board stuff when I'm not using my CNC router. So we're going to get that all attached on here. But before we get to that point, I think it's probably best that we go through. I've did a kind of a time-lapse type filming sequence to assemble all of these components and get them to this stage. Assembly isn't that difficult, but I think it'll just pay to go through that. I'll voice over it when it's going on fast forward, and hopefully it won't take much more than 5-10 minutes or so. So let's dive into that right now. Getting started, I laid out all my components on my workbench here. I've got, you can see I've got DuPont connectors, and I'm creating a couple of cables. I opted for that. If you're not, don't have the stuff to do, DuPont cables, etc., you can use prefabricated ones, and you might have to get a little creative with that. But just go ahead and create your cables, make them at the length that'll work for your setup. Now this is what the internal housing looks like, or bracket if you will. All the components actually attach to this, and then it slides into the outer housing, which is a bracket to mount it onto the machine and so forth. So I'm just kind of going through showing you how all the components fit on this device. And as you can see, it's very compact. And in truth, the hardest part of this whole assembly is managing the cables. The display mounts inside there, kind of like the Pico does with the small sheet metal screws. Making up some more cables and shortening the ones that came with the display so that I can get them routed properly and still get it all to fit inside this bracket or internal housing. Here you can see how tight it is, getting the components to fit inside. This will be the cable that goes out to the remote sensor with the RPR220 on it. Just showing you here its size, also noting the beveled edge in the one spot, which helps guide you as to which pin is which, and that helps, of course, for getting the wiring done in this area. At some point, once I'm comfortable with the full assembly, I'll put some hot melt glue in there to help secure the cable so it's got a little bit of strain relief capability. This is probably a cut-off USB cable, or it could be an old mouse cable. I often save a lot of those because I find them really handy for situations just like this. Moving on, I'm putting more DuPont connectors onto this particular cable. Of course, you can always solder things directly too. That just makes it very difficult to disassemble things for maintenance and repairs and tinkering. A lot of these places you're going to see this little black vise with a red screw on it. That's a 3D printed vise, and in truth, that thing has been very, very handy. I'm using it a lot on the bench right now. If people are curious, you should be able to find that on Thingiverse. I downloaded it, printed it, thinking it was more of a novelty. Turns out it's a useful tool. Now moving into our final assembly with all the wires there. And you can see I'm very carefully manipulating all the wires, trying to get them to fit while I slide in the Pico. Now I got to very carefully try to get the screws down in there and tighten them up. Finally getting the display to feed through with our cable through the mounting housing. And then finally we're getting the front cover on. You may call that a bezel, or depending on the world, either a bezel or a bezel. And that pretty well gets the assembly wrapped up. Now we'll just reflect back onto the schematic a little bit. It is a Fritz Inc. schematic, so there's good and bad with that. Unfortunately, what I have tried to do in the past with this particular object, the display icon or whatever you want to call it here, for some reason it won't let me save this whole file and distribute it to you. It turns this into a Raspberry Pi Pico. So unfortunately, this had to be converted, or this whole schematic had to be converted to a PDF, but nonetheless, I'm including it in our documentation packet on the companion website. But just follow the schematic here. This resistor for the LED, the infrared LED, is 330 ohms. Doesn't need to be necessarily that much resistance, but it was what I started with, and I got very good performance using that value. Over on this side, with some experimentation, I found that anywhere between 39 and 47 k ohm, this resistor worked out very effectively, giving me good crisp on-off signals for me to interpret with the Pico. And that's basically how I wired up the actual physical device. Now let's turn our attention back to the assembly. And one of the things that kind of bothered me, and I hope I can get this to show up good on the camera, but 3D printing is wonderful, but there's just certain aesthetics to it that frankly suck. Yes, I know you can do ironing and so forth to get your top surface layers to look better, but it doesn't always work, especially on small objects like this with a lot of detail. And you can see these areas here just look terrible. It is a pretty sharp edge here where I've got the beveled edges on this slight raised area. And in here, this large chamfer or beveled area, just doesn't look good. So for me, it really kind of ruined the look that I was after when I envisioned this whole design back in January or February when I started on the project. So that I had put it all together, and I filmed that other sequence, the assembly sequence, a while ago. It's probably several months ago. And so I've been stewing on it. It got to me enough where I came up with a different idea on how to make this piece. Fortunately for me, I've got a CNC router in my shop. I built it a number of years back and have been updating it and so forth in some other videos here on the YouTube channel. So if you're curious about it, be sure to check out those videos. But I thought I can probably do better than this, so I just took a stab at something. I had this piece of corian, which is solid surface material. It's artificial material or a fabricated material, composite, if you will. It's like a plastic, and I believe its origins are in dental false teeth or something like that. But it works, people use it for kitchen and bathroom countertops a lot. It was very, very popular about 20, 25 years ago, and today most of it's been replaced, or the alternative now is more in the granite, marble, hard stone device, or subjects like that. But I thought, I bet you I can machine that pretty good on the router, get better detail, and have less surface imperfection and not have to spend a lot of time finishing it. So what you're going to see is basically right off the router and just spray painted with a light coat of acrylic black. And hopefully I can get this to see. Here you can see the surface texture of the topmost surface. And it looks like it's a little scratched up because the stone that I had, or the whole raw material, had some scratches on it. And then down in here, you can see the area where we machined. Now, all of it was machined on the outside, the inside, this bevel area. You'll see it's still got a little bit of faceting in there, but I didn't do anything special for the model to make that surface smoother. In other words, reduce the faceting and so forth. But nonetheless, even in this rough state, this looks a whole lot better to me than this one. So this was going to be my last change. So I'm going to pop this one off, put this in, and then we'll move on with the project. And I'll give you one look at that before we move on. At some point, I'll learn not to continually use black for some of my projects, because a lot of detail is lost while we're filming. You know, once the camera sees it with lighting, etc., you kind of lose a lot of little detail. It's hard to see that with the camera and so forth. So I did do a project a little while ago, that turntable for photography. I assume that's already out by now. I did that one in black and filmed it all, and I ended up redoing it again and printed it out in silver PLA so that you could see the details on the inside so you could understand the assembly. But that, let me get the thing running again here. And I just like the looks of that a lot better than that 3D printed thing. Like that, I just wasn't working for me. And I wanted this to look, if you're wondering the styling or whatever, I wanted it to look like an aircraft, a full-size aircraft instrument. This would be a style that's used a lot, not in the modern commercial jets where they're using digital displays and so forth, but probably very early days of aviation, all the way up to probably still current, you'll find instruments on the dash that are housed in a housing that looks a lot like this. So it was a good look for me. That's what I liked. Hopefully you guys like it too. Here it is, all mounted up on the drill press. We'll get you some close-up footage of it in a minute. For calibration, I verified it against a known reliable source, this little handheld digital tachometer. Used this for a good number of years now. So my tachometer is about, 10 or 20 RPM off. Of course, the RPM floats a little bit, so it's hard to follow it perfectly. But we'll show you it in operation here just for a moment, and then we'll dive right into the code to see how it all works. Okay, now we're back into the code here, and a lot of this code is already existing and already explained in the previous other videos related to the RPR 220 video, and then the two videos covering the Waveshare 1.28-inch round display. So we're going to kind of gloss over those. And then some of the stuff that is added here, I'm not going to go into super detail. It's a lot of geometry. But if you want to dive into it, I'd say extract it out of here. You don't need a tachometer to explore it further. It's just a matter of understanding basic trigonometry as how I'm plotting things along an arc. So I'll kind of touch on that when we get into the code. We're going to do some imports, machine thread, SPI, etc. I'm using several different time libraries for different purposes, probably pretty sloppy technique. Live with it. It fits in memory, so I'm not going to sweat the details, so to speak. Here we're importing the Russ Hughes library, and then a couple of fonts that I kind of got in there primarily for something I want to try in a later, perhaps, update of this device. But for right now, I just wanted them in there as a placeholder, so to speak. But these are kind of used to help define limitations of the graphics and how I can calculate the position. There's a pointer that spins around the dial to indicate the RPM, kind of like a needle. And that's what some of this is for, is to figure out that scaling from RPM to pixel coordinates on the little display. This guy up here is really one of the workhorses, and it's a function that is running in a thread. We initialize it almost at the bottom of this whole thing here, just before we get into our endless loop. We initialize it here. So let's go back up. And here we again are importing the photo pin. And because it's in the thread, the threads seem to really need everything imported locally to them. So it's imported there along with microtime, variable global RPM, which allows me to communicate across the thread. And then several variables that are used internally to count clock ticks for measuring time that is passed. And then a cycle time, which is how I know the duration of a certain number of a duration of time, so that I can do calculations based on that. But inside this thread function, we are running an endless loop here as well. So two parallel, so to speak, endless loops, one running in, say, core 1 and the other running in core 2. Right here, we're looking for the transition from of that input signal of our photosensor, going from high to low or low to high. In this case, we're rising, so we're going high. We're going to update the previous state so that we can look for this toggling effect. Because as the spindle is rotating around, this signal is going high, low, high, low, high, low, obviously very, very fast. And that's what I need to watch for, is when it goes high, and then I can start a counter here, temp st, and record the current time and ticks in microseconds. And then from there, I can calculate the RPM, taking the cycle time, 1 divided by the cycle time times, you'll see this, we're going out into the microsecond, and then we're going to multiply that times 60 to get it up into the minute. Remember, this is minutes, this is microseconds, etc., so you got to do that balancing there. But that's what's going to happen when the pin rises from low to high. When it goes low, We're going to reset the pin was variables so we can track high and low and what the previous state was. But when it goes low, we'll record the start time from the temp start time up here. And that'll give us that cycle between off to on. And then down here, this is kind of a catch-all, just so that I could get the tachometer to read a time constantly, or I'm sorry, a speed constantly when it's at 0 speed. So if the time is extremely long, we'll just set the RPM to 0 because it's not going to be effective below 1 RPM, so to speak. So this is running in a thread. It runs very, very fast, and it's taking care of a lot of the computational stuff. A lot of this code here goes all the way back to both the first and the second videos I did on this Waveshare 1.28-inch round display. So this code was just covered, so to speak, in there. We needed to, this function just basically gets the endpoints of a line given an angle, so it has to do basic trigonometry. This line here is this function is going to plot an arc line, and it does that by drawing small linear segments, and that's what this is about. This is that from the second video I did on how to create your own font. And this is the, I call it a 7-segment looking font. And that's the one that you see in the center of the display when it's running. And this is the good bulk of the code here. And that was all explained fairly well in detail in the other video. This little, actually, this one here was also just covered in the previous video because this is what starts it. We're going to plot the characters starting at a certain position up to, in this case, 6 digits. And just for reference, on this little drill press, max RPM of the spindle, I think, is in that 12,000 range with the power supply, etc. I've got on here. It only runs up to 11,000. But I do remember when I was doing the research on this, or my early testing and so forth, it was real easy to get a false reading or a fake reading to go much higher. On this housing up here, this fan housing, there's one area where the black tape is missing. I'll get a close-up photo of that so you can see it. And that's how what we're triggering on when the photosensor sees that, and then it goes black on the black tape that's on here. And of course you can use paint or whatever, it doesn't really matter. But the way to trick it was this. When we're counting right now, we count every time that shiny spot passes by our sensor. Well, if I have more than one shiny spot, it will interpret the RPM faster. And I do remember having 4 spaces on there in my early testing to see how fast of a spindle I could get to read reliably. And I believe I was in that 30 to 40,000 RPM range, which to me is insanely good for what we've got going here with the code and the little Pico, etc. Now, I know it can even go much faster if we get into PIO and assembler and so forth, but for the way this was structured and how I wanted to do it with MicroPython, I was very impressed with that performance. So now we'll come down here. This is something that wasn't in the other graphic programs. And it's just plotting a pointer that goes around the outside of the dial. And you would have seen that when it was running earlier, and I had a close-up video of it. And that's just a matter of what we're going to do. I'll explain it in general, not detail. We're going to move that pointer to a position that's scaled along that arc based on the RPM scaled to the number of degrees. Now, if that has not moved, say the RPM is the same, well, then I don't erase it and replot it. If it is different, then I'll erase it and replot that little pointer or triangle. And that minimizes, one, the amount of work you're doing on that function, and it reduces flicker. And it can get very annoying if you don't handle this stuff where it's just something on the screen doesn't need to be redrawn. Don't redraw it or erase it and redraw it, because oftentimes you'll just get into some really nasty flicker and it's just unsightly. But essentially that's all this function does, is it looks to see what the RPM is. If it was different, I'm saying absolute position of the old pointer and the new pointer. If it's different, erase it and then redraw it at a different location. And that's what all this is down here. Lots of trigonometry in converting from radians to degrees, etc. If you are into graphics and so forth and drawing them, this is, I'm going to say it's rather crude code, but it's very simplistic. It's low-level trigonometry or geometry, but I think if you've had that, which you should have probably in high school and so forth, this will look very, very familiar to you. This section here, we start up the SPI interface and get everything configured for this particular display. And this one here was a function from the original videos I did on the Waveshare display, and a little bit of decoration on top of it. There's an arc on here to draw some of these outer lines around the display there, and to make certain areas yellow and red for our red line on the tachometer, and that sort of thing. But if you're curious about this is a lot of fun to play with. If you got a display and you want to tinker around drawing and such, it's a lot of fun. It can certainly suck a whole weekend away from you if you get into it. Down to our final section here. This is where we start that thread that's doing all the work of checking the sensor, reading it, and then calculating the time it takes for basically an on and off signal to figure out RPM. Before I go into the main endless loop, we're going to draw the background, set the RPM to a default value of 0. We'll display that, and then we'll plot our pointer. Finally, we get to the endless loop down below. We're going to display the value of the RPM at this location. We're going to plot the pointer, and we're going to sleep for 100 milliseconds and just go around and around in a loop. So that display is updating at 10 times a second, but you don't see any flicker because I'm not constantly erasing and redrawing. I'm only try to do an erase and redraw when a number or a position of some graphic element changes. So keep that tip in mind. It'll help you a lot with messing around with graphics at a primitive level, so to speak. And then these were just notes to myself to figure out which way to rotate the display, the graphics on the display. Most often, LCD displays allow you to rotate the orientation of the graphics relative to the physical display. And that's the whole program. There's a lot there, and most of it has already been covered in 3 previous videos, so I didn't really want to go into a lot of detail and drag this out for a 3-hour video, because I know everybody will bail out on it anyhow. Well, I think we'll wrap up this video here. It's probably very long, and I don't want to have it get too long. Hopefully it sparks a little curiosity on your side to work with graphics using the very simple primitives that are that you can utilize to draw images and so forth on your displays. Perhaps you have, and I know several of you have already requested it, so for your tachometer projects, this is just one example of how we can implement a tachometer using the Raspberry Pi Pico and these really cool round displays. And I think I pretty well captured the look of the display, or the housing, as an aircraft instrument. I know it's not an aircraft, but it's just a style that I really liked. So that'll do it for this video. Thanks a lot for watching, and I look forward to seeing you in the next video.